Now I'm excited to introduce our first finalist for the Discovery Prize, Dr. Jennifer Cano. Dr. Cano joined Stony Brook University in 2018 as an assistant professor in the Department of Physics and Astronomy, and she currently holds a visiting scholar appointment at the Flatiron Institute in New York. Her research is in the field of condensed matter theory, delving into fundamental principles such as classification and predicting new material platforms to realize exotic quantum phases. She developed the theory of topological quantum chemistry, which combines group theory, topology, and chemistry to predict new topological materials. The title of her presentation is Theoretical Framework for the Discovery of Topological Moire Materials. Please welcome Dr. Cano.
Probably most of you have one of these in your pocket. But have you ever thought about how much energy it consumes? In fact, phones, computers, and the networks that power them make up 10% of global energy consumption. That is a lot of energy. It's on par with the airline industry. Thus, it is imperative that we develop energy-efficient materials to power our devices. So where is all this energy going? Well, when electrons travel through wires, they bump up against each other, and they bump up against the walls of the wire. And all of those collisions cause heat, which is wasted energy. We call it dissipation. You can think of this like when you're traveling in heavy traffic. Even though everyone wants to move in the same direction, there's still collisions, and those collisions waste time and energy. This should be contrasted to the Autobahn, which is the German highway system known for highly efficient transport. What we need is an Autobahn for electrons. But is a dissipationless wire even possible? Well, we know one place where it exists, and that's a superconductor. But superconductors have a different problem. They only operate at very, very low temperatures. And so that doesn't help us. We need a new solution. The solution that I propose is a phase of matter that occurs when you put a thin slab of material in a large magnetic field. When this happens, the electrons in the material feel a force from the magnetic field, and that makes them want to move in circles. And when the magnetic field is very large, it actually forces the electrons to move without any collisions, thereby creating a perfectly conducting wire, a dissipationless wire on the edge of this material. This is an amazing effect. It's called the quantum Hall effect, and it was the subject of 2 Nobel Prizes. So with this perfectly conducting wire, does it solve our energy problem? Not quite, because it requires this large magnetic field. This is the sort of magnetic field that is so large, it will ruin your credit cards, it will break your pacemaker. It's not the sort of magnetic field that you want in your pocket. So this begs the question, can we separate these ingredients? Can we have our quantum Hall effect without the large magnetic field? This question was answered in a seminal 1988 paper. And there it was shown that theoretically, yes, the quantum Hall effect can exist without a magnetic field. But the author of that paper did not know any materials that would realize this phenomenon. And so for the next 25 years, scientists have been trying to find materials that can realize the quantum Hall effect without a magnetic field. And during that time, there have been many breakthroughs, but I'm going to propose a different approach. I'm going to propose that instead of looking for materials that realize this phenomenon, we build them from the bottom up. And since the quantum Hall effect requires a thin slab of material, our building blocks are going to be the thinnest possible materials that are just 1 atom thick. We call these 2-dimensional materials because electrons can move sideways or front backwards, but they can't move in the 3rd dimension. So do 2-dimensional materials exist? Yes, they do. The most famous of these is called graphene. Graphene is made of carbon atoms, which are arranged in the honeycomb lattice that you can see here. When graphene is stacked in its three-dimensional form, it forms graphite, which is the common ingredient in pencil lead. But in its two-dimensional form, graphene has amazing electronic and structural properties. It is extremely strong and extremely flexible, so much so that if you made a hammock out of graphene, it could support the weight of a cat, even though it's thinner than a spider's web. This is an amazing material, which was the subject of another Nobel Prize in 2010. And the discovery of graphene launched the whole field of two-dimensional materials. And now there's not just one or two or three of these materials. In fact, a recent database predicts that there's over 6,000 two-dimensional materials. This is a huge playground for us to find our perfect conductor. Two-dimensional materials also afford us another possibility, which is we can stack them to make new materials whose properties we can tune by design. This materials by design principle has often been compared to playing with Legos, because with a few simple ingredients, there's so much that we can build. But there's one thing that we can do with our two-dimensional materials that we can't do with Legos. Legos have to be stacked aligned with each other. But two-dimensional materials can be stacked with a twist angle. See what happens when you change this twist angle. As the twist angle is varied, you see an interference pattern. And that interference pattern dramatically changes size. That interference pattern that you can see with your eye, electrons also see that interference pattern. And so as the twist angle is varied, it can dramatically change the electronic properties of a material. In 2018, it was shown that if you stack two layers of graphene and you change their twist angle from just 0 to 1 degree, that material can change from being a metal to an insulator to a superconductor. And the following year, it was also shown that that same material could realize this quantum Hall effect without a magnetic field. So this was an amazing breakthrough. But it's plagued with its own problem, which is that it also is limited to low temperatures. And so this makes us wonder, with all of these 2D materials and all the ways that we can stack them and twist them, there must be somewhere in this large phase space where we can find this effect at a higher temperature. The problem now is that we don't know where to look. So what we need is an instruction manual. And this is where my work comes in. So I'm a theoretical physicist. So what I want to do is predict the properties of materials computationally. The problem with these twisted bilayers is that they're so complicated. Their repeating unit from this interference pattern contains so many atoms that we don't have the computational power to run the algorithms that we would like to run. So we need a new approach. And that new approach takes the form of an algorithm that my team published earlier this year. So our algorithm has 3 simpler ingredients. The first ingredient is the electron wave function in one layer. That tells us how electrons behave when they move around in just one two-dimensional material. And this is something that's easy for us to compute because it just involves that single layer. The second ingredient is how electrons tunnel from one layer to the next. And this is also easy for us to compute because we don't require that those 2 layers be twisted. And finally, the third ingredient is the size and orientation of that interference pattern. And this is what allows us to interpolate, to take our results from our first 2 ingredients and turn them into properties of our twisted bilayer. So with these 3 ingredients, our algorithm can efficiently predict the properties of our two-dimensional twisted materials and efficiently predict whether we'll realize a perfect conductor. So we've tested this on a couple of examples, but what we want to do next is to interface this algorithm with the database of thousands of 2D materials. The result will be many new predicted perfect conductors. This will serve as our instruction manual. We will hand over our predictions to our experimental colleagues who can validate them in the lab. And in the worst case scenario, they don't find any material that performs better than twisted bilayer graphene. But the dream is that they will find one or more materials that will realize this quantum Hall effect in zero magnetic field at room temperature. This discovery would dramatically transform modern technology. And it's this material that would serve as our Autobahn for electrons. And this material will be the backbone of the next generation of energy-efficient electronics. Thank you.